thank you, Chris.
Sorry, you have 12 minutes plus 3 minutes question.
Yeah. Can everybody hear me well? Yeah, all right. So it's a pleasure and honor to be here today. Of course, I'm here on behalf of our team, and the team consists of Matthias, Jelko, and myself. So Chris already had a very nice introduction what the aim of the challenge was. So we want to basically solve an optimization problem. I prefer to minimize instead of maximize, but that doesn't matter, right? So we want to optimize Poisson log likelihood or negative Poisson log likelihood and prior or a regularizer, right? And the aim of the challenge, as Chris said, is to do that as efficient or as quickly as possible with respect to reference solution up to a given tolerance, right? So I guess that's a very practical approach, right? And then we have seen already the formula for the relative difference prior. I think, Chris, you had an error here, so you had a square root here, but I just checked the implementation. There is no square root here. Yeah, so if there is, I think, yeah, our method shouldn't work, but okay, I think there isn't a square root. Okay. Anyway, so the general approach that our team submitted in the end is preconditioned stochastic gradient descent, right? So our update looks like this. So we calculate our new solution based on our current solution minus stochastic gradient of our objective function evaluated at the current solution times the diagonal preconditioner times the scalar step size, right? So basically we have to understand the three terms. So the first thing to understand is how do we calculate this stochastic version of the gradient, right? And the thing that makes it fast is that in every gradient evaluation, we only use a subset of the data, so we only have to do a subset forward projection and a subset back projection. Then we have to talk about what is this diagonal preconditioner and what is this scalar step size, okay? So the first important term is the stochastic gradient, and then we're using a technique that was originally published, I think, by Johnson and Zhang, right? And then Robert Tweinman, PhD student from Chris, had a very nice paper who applied that to path reconstruction. And so what you have to do is shown here in this complicated algorithm, but if you zoom into the details, you have two important lines. So it shows you if you want to calculate the stochastic version of the gradient, what you have to do is you have to calculate one gradient with respect to the subset or a subset of the cost function, so that means subset back projection, subset forward projection, and then a bit of simple math, right? So you have to store a few extra images, which you subtract and add, right? So, but basically the computational work is in here, right? Okay. And what are those extra images? Those G images, right? So those are basically the gradients with respect to all the subset functions, okay? So what you do is every once in a while in SVRG, you calculate all those G images, which is basically the computational effort is one complete forward projection and one complete back projection. But you do that only once in a while, so we do that every 2 epochs. And for all the other updates, you just have to calculate a subset gradient, which is much faster. And so why did we decide to SVRG? Because we read Robbie's paper, which is very well written, and the notation is very clear. So for us, it was very easy to implement that, right? And so Robbie could actually show that, so SVRG in terms of convergence seems to be promising. He also suggested or used another algorithm called Saga, but we didn't implement that one. So if you read the discussion of Robbie's paper, it's mentioned that they observed that the performance of stochastic algorithms was impacted by the choice of step size and preconditioner. The optimal preconditioner is the inverse Hessian of the objective function, but this is hard to compute, okay? But obviously, you know, probably you know it's worth looking into, you know, getting a better preconditioner and finding a somewhat smart rule on how to choose the step size. Okay, so this is what we did. So we were actually, in the end, we were working on a better preconditioner, and to be fair, this is not my idea, so this is the original idea of Johann Hertz, who published that already 22 years ago. So the motivation goes like this. We already heard in the first talk by Andrew Wieder that if you just want to optimize the negative Poisson log likelihood, right, and you do MLEM, you can view MLEM as a preconditioned gradient ascent or descent, right? And this diagonal preconditioner has this form, right? So it's the image divided by a joint of the forward model applied to sine wave of ones, right? So that works reasonably well if you only want to optimize the negative Poisson log likelihood, so data fidelity. So on the other hand, you could say, so what would we do if we would forget about the log likelihood and we would just want to optimize our prior? you could say, well, in the ideal case, we want to do a Newton-like update. So what we need to do in the Newton method is we need to calculate the Hessian, so the matrix of all the second derivatives. And then we have to invert that, right? So, and that's, of course, not feasible. So calculating the Hessian is already a lot of work, but yeah, inverting that giant matrix is completely unfeasible. But what you could do is, you could say, well, maybe what we just, approximate the Hessian by the diagonal, so the main diagonal of the Hessian, right? And if you do that, of course, that is very easy to invert, right? So you just divide by that, okay? And then, well, so this is just written here, what you have to calculate, right? So the diagonal of the Hessian, right? And if you do that, that is not so hard. So if I say not so hard, that was very easy for Matthias, who was a mathematician. So that took me, I think, 2 to 3 hours in a long train ride that I did to Germany, right? But this is the solution. So you arrive with that term, which is easy to implement and efficient to calculate. And we even do that in CUDA, right? So this is very fast to calculate. And what we do then is we say, look, so this is basically our proposed, or this is one way to precondition the update for the prior, or basically the gradient for the prior. This is the preconditioner that you want to use if you optimize the Poisson log likelihood. So let's try to combine them, and let's try to combine them in a conservative way, right? And the way we combine them is by taking what people call the harmonic mean, right? So if you write it, you can write it like this, right? And basically what happens is, if the prior dominates, right, if D prior is much bigger, then you end up with D data, and vice versa, right? So if you write it out, you end up with this preconditioner. So this is a formula to something that Johan already published 22 years ago, okay? So this is the theory, right? So that sounds all very nice and convincing, I hope, but what we actually implemented after analyzing all the data sets that we had for training is, so we have a little fudge factor in here, so this is a factor of 1.5, right? So I guess this is due to the fact that, yeah, there's more than the diagonal in the Hessian, right? So there's this fudge factor. And if you look closely, I put this subscript SM, so smooth in here. So what we do is we smooth our images a bit before we calculate the preconditioner. So that's not entirely clear to me why that is needed, but I have observed artifacts if you don't do that. I think that could be due to the numerical stability of those calculations of the Hessian, right? Because especially if you're in a background where everything is close to 0, you can get strange values in here, right? But this is basically more research has to be done in the future why we need that, okay? So this is just to show you, like 22 years ago, basically Johan suggested something very similar, right? So this formula is something very similar that I just showed you. Okay, so we understood how we calculate the preconditioner. Maybe to convince you that, I'll show you what the effect of that is. So I'm showing 2 data sets. So this is the first data set. So this is data from the Siemens MMR and the famous NEMA IQ phantom. If you just look like at the diagonal preconditioner that basically that we usually use for optimizing the log likelihood, that looks like this. So this is basically the image divided by A transpose of 1, right? If you compare that to our proposed preconditioner, you can see the effective preconditioner is smaller, right? Okay. So if you look at the ratio, you can see the ratio is between, so it's on a weird color scale, but the ratio is between 0.2 and maybe in the center 0.5, right? And if you remember from the first slide, I said what we're doing is the step is basically alpha times a preconditioner. So if you would keep alpha the same, so alpha equals 1, for example, you would do a smaller step with the proposed preconditioner in that case, right? Okay. Obviously, this balance between the diagonal preconditioner for the data and for the prior depends on how strong the prior is, right? Relatively speaking to the data, right? And so what I've shown here is this is the second data set, the NeuroLF Hoffman data set. And here you can see what actually is going on is that the proposed preconditioner is almost the same as the data preconditioner, right? The ratio is very close to 1, right? And that's because I think, relatively speaking, the prior there is much weaker, right? So you're basically doing the original step using the original preconditioner, okay? What's interesting, what we tried first is before we implemented the better preconditioned SVRG, we just tested, obviously, SVRG using the normal data preconditioner that also Robbie used in his paper. And what you can see is, if you use a fixed step size of 1 here using that preconditioner, you get divergence, right? So that somehow shows you that 1, or the scalar step size of 1 is too big, right? If you do it with the NeuroLF Hoffman, you get convergence, right? In Neuro Hoffman, I think you can get even away with the scalar step size of 3 and using the diagonal preconditioner, right? And so that but that shows you that basically, a good step size is strongly data set dependent, right? So, and we hope to capture that data dependency using that better preconditioner. And then, so the last important thing was basically the step size, which is shown here in the middle row. So what we did in the end, we submitted obviously 3 algorithms because we were allowed to submit 3 algorithms, right? But the difference between the algorithms is very subtle, so they all use this general scheme. So one difference is on how we set the step size alpha. So in the first naive version, we basically have a hard-coded step size rule. So in the beginning, we're a bit greedy. We say, in the first 10 updates, use a step size of 3, then we decrease it to 2, 1.50, and in the end, we want to be safe, so we say, okay, use 0.5. I think even if you don't go to 0.5, you still get convergence, but it's just to make sure that, if we have a weird unseen data set, decrease the step size, right? And the second algorithm uses a more sophisticated way. So what we do is we also start with a step size of 3, but then we calculate or evaluate the step size rule, which is called the Barzilai-Borwein step size rule, which in principle could increase or decrease the step size, but we only use that to decrease the step size. So if that step size rule says, you have to decrease the step size a bit, we decrease that, right? We never increase the step size. Okay. And then also, what obviously is also important is how do we choose the number of subsets. So what we always do is we take the divisor of the number of views that we have in the sinogram that is closest to 25. So we always have around 25 subsets, right? And in the first algorithm, and also in the second, we do the subset selection is purely random, right? And then in the last algorithm, we have 2 modifications. So it's very similar to the second algorithm. We use slightly less subsets. So it's the closest divisor closest to 24.2, which in some data sets then decreases the number of subsets, okay? And the subset selection is still random, but there is a bit of orderedness in the steps in the subset selection, right? Okay. So what I will also show you is, obviously this is what we submitted, but we tried obviously much more things, right? So because we had 3 very talented people in the team, right? So first of all, what we also tried is we tried different ways of this conservative combination of the diagonal data preconditioner and the prior deconditioner. So we tried an element-wise mean, but that didn't work very well. We tried different approximation of the inverse of the Hessian. So for example, by the Woodbury matrix identity. Don't ask me what that is, so you have to ask Jelko what that is. Yeah, but that also didn't work very well. Then we tried different subset or smarter subset sampling strategies instead of just random sampling. We tried rules that are basically related to the norm of the subset gradients, but that gave no real performance gain, and since you have to do additional combinations, we stopped that. And obviously, since we had me and Matthias on the team, right, we also tried primal dual methods, but the problem is with the relative difference prior, there is no analytic solution for the proximity operator, so we have to do numerical approximations, and that becomes slow, so we also gave up on that. But I would say, if you have a prior where you can efficiently evaluate the proximity operator analytically, those methods can be competitive, right, but not for that challenge. Okay. All right, and finally, I want to say a big thank you to many people. So first of all, Robbie for writing that paper on stochastic gradient methods, and Pat, because that was so well written and so clear that it was very easy for us to implement SVRG, right? So it's few lines of code. Then obviously Chris and Casper for setting up the challenge, right? So that's an enormous amount of work, and I really enjoyed that I could appreciate in that challenge. And then last but not least, obviously big thanks to Johan, who isn't here unfortunately this year. Not sure if you know, but Johan just retired in October. I can assure you that he's still doing a lot of research, and I think there's a big chance that he will be at the MIC next year in Yokohama. Okay? And finally, obviously, a big thank you to my teammates, Matthias and Jelko, and now I'm happy to answer questions.
Any questions?
Very nice work. So I have a small question. So one slide you show the hybrid preconditional, and you use 1.5. Could you elaborate a little bit more on your choice of 1.5
That's heuristic. I tried also 2, 3, and 1, right? And based on the training data, I think 1.5 gave the best results. So I'm sticking with 1.5. I think Johan has some hand-waving arguments. It should be 2 because what he published in his original paper is probably not 100% correct. But in the end, yeah, that was optimized on the training data that we had at hand. Yeah. Well, if someone is better at mathematics and maybe can prove why maybe it converges with a factor of 2, that would be nice. So maybe as a disclaimer, right, there's no strict mathematical convergence proof, right? This is just, we tested it on many data sets and it seems to work.
Yeah, maybe a quick question. When Robbie is writing the paper, he had some problems with the X term going to 0 too fast in some sense.
Yeah, okay, so sorry, so this is sloppy notation. So this, what I call X smooth here, is actually a smooth version plus a small delta. So this, I'm doing I tried it also without the delta and gave very similar performance. I'm not sure if it's needed, but yeah, there is a small relative delta that we just did. That's true.
Okay, thanks again for the very nice talk.